In this last set of videos under linear algebra, I've been considering advanced and applied linear algebra. So we've seen linear algebra in data science. In the last video, we saw linear algebra in computer graphics, where we saw um, pipeline transforms and homogeneous coordinates. So here we're looking at linear algebra in differential equations. This is a more familiar terrain because I've made a couple of playlists where we had to use matrices to solve. I have a full playlist on differential equations touching ordinary differential equations and partial differential equations. So here, in the spirit of linear algebra, we're looking at linear algebra in differential equations. Okay, so I'm basically will be considering two things, namely matrix exponentials and systems of ODEs. So the motivation here is that many real-world systems involve several interacting variables. Like when you talk about population models, electrical circuits, mechanical systems, chemical reactions, these systems are written as, you can write them as systems like systems of equations that we've been like some that we've seen before. So you have x1 prime of t equals a11 x1 plus a12 x2 all the way down. Then you have x2 prime of t equals a21 x1 plus a22 x2, and things go on like that. And then you can always represent them concisely in matrix form like x prime of t. Now it becomes like a system. So x prime of t, in x prime you have x1 prime, x2 prime, and all the way down. So x prime of t equals x of t, where x of t is all this x1 of t, x2 of t, down, down, and then a, the matrix A now is the matrix of coefficients here. So you have A11, A12, A21, A22, all the way down, depending on the system of equations you have. So this is called a linear system of differential equations. Okay. Now we have a scalar case of this. If you consider the equation x prime equals ax of t, its solution is simple and it is x of t equals CEA raised power t. This motivates the matrix case where you now have x prime equals ax of t, whose solution is x of t equals a raised power t, x of 0, like that. So this gives the idea. By the way, if we want to just refresh our memories about differential equations, you have x prime of t uh, equals ax of t, right? X prime of t. So you have x prime of t equals, um, not the matrix thing now, equals ax of t. So in short, you can write that as x prime equals ax, right? So how do you take care of this? This is as good as saying dx dt is equal to ax. So we can do division, we can divide both sides by x so that we have dx over x equals a dt. So if that happens, we can integrate both sides. So we have integral of dx over x equals a integral of dt, because of course a is constant. So, and whenever you have integral of dx over x, right, this is more or less like if you integrate 1 over x, that's ln x, right? Ln x, and this is a. If you integrate dt, you get d. You get t. Integrate d anything, you get that thing. So this is t, and that has to come with a constant. All right, call that k. So that's the constant of uh what is it's called? I'm trying to remember that constant now. Have I forgotten that? It's it's a constant to make up for arbitrary constant. Yeah, that's the word I was looking for. Arbitrary constant. So, but don't forget we are trying to solve for x. And the way to solve for x is this x is attached to Napierian logarithm. So to remove Napierian logarithm, you need to take the exponent. So e ln x is now e raised power at plus k. So an e ln x simply means x simply, and that then you have e raised power at plus k like this. So, and then you can go forward to say this is now x equals e raised power at multiplied by e raised power k. So e raised power k is a constant right here. So if you let c be e raised power k, or call it anything you want to call it, so x now is equal to c e raised power at. Okay, c e raised power at. But of course, if you want to get rid of this constant, you need initial conditions. So if you don't have initial condition, you can leave it in this general form. So it means that X is a solution, is a family of functions, and that is decided by this C. So you can have different C's, different graphs as C varies. But if you have initial condition, you can get a unique solution, right? Instead of this general one like this. So from that idea is where we got so we can then have the motivation for the matrix case where we now have X prime now matrix equals A. A now becomes the matrix of coefficients and then multiplied by X. So in this case, the solution now looks like e raised power 80 now, where A is the matrix still. And you have X naught, that's the initial condition. All right. So now let's talk about matrix exponential. So for a square matrix A, we can say e raised power 80 is equal to 1 I plus I plus 80 plus 80 squared over 2 factorial plus 83 raised by 3 over 3 factorial plus all that. Now, this looks familiar if you remember the idea of exponential equations, right? Imagine if you have e raised power x, e raised power x is simply the same thing as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus all that. So this looks like if you now have e raised power 80, okay? So that's like 1 plus 80 plus all that, all that just keeps going like that. So 80 squared over 2 factorial plus 80 cube over 3 factorial and things like this. So that's the idea here. So this is analogous to e raised power x, right? That's exponential expression. So the properties now, it always converges and then produces a matrix and solves systems of ordinary differential equations. In this case, that's the matrix exponential has all these possibilities. So always converges, produces a matrix, solves systems of ordinary differential equations. And then we have the fundamental property. If x of t equals e raised power 80 multiplied by c, then x prime of t is actually ax of t. Therefore, the solution is x of t equals e raised power 80 times x of 0, the initial condition. So for solving linear systems now, we solve x prime equals ax and with initial condition x of 0 equals x naught. So the procedure is, first of all, we compute e raised power 80 multiplied by x naught, and then we simplify. That's how to solve linear systems using this. And then we also talk about diagonal matrices. So if A is a diagonal matrix of eigenvalues, so you have A is lambda 1, 0, 0, lambda 2, and that means that e raised power 80 will just be e raised power lambda 1t 0, 0, e raised power lambda 2t. So corresponding e raised power 80 corresponds with the lambdas like that. So these are diagonal matrices for the original matrix, and then it's the exponent of the matrix. Look at this very sweet example. If you have x prime to be 2, 0, 0 minus 1 x, that's like x prime equals ax now. This is the matrix 2, 0, 0 minus 1. And then you have this initial condition, meaning that at time t equals 0, the value of x is 1, 2. So in this case now, if you do e raised power 80, so if you follow this now, that means you have e raised power 2t, 0, 0. So for 2, you have e raised power 2t. For minus 1, you have e raised power minus t. Okay, so then x of t itself now will be e raised power this one now e raised power 2t then 2 e raised power minus t based on all these ones now. So that's how x of t goes in that case, because of course that's the initial condition now. So if you put 1 2 here, so 2 0 0 minus 1 multiplied by 1 2, okay, that'll be I mean e raised power 80 multiplied by x naught rather. Maybe I should just do that. It's just very straightforward. E raised power 2t 0. Okay. Um, e raised power 2t 0. You have e raised power 2t 0, 0, e raised power minus t multiplied by 1, 2. So here you have two rows. It means you're going to write this one twice. So you have 1, 2, 1, 2, and then put this over it, e raised power 2t 0, and here you have 0, e raised power minus t. So if you put all that together, um, you know, this would be e raised power 2t up there, and 2 e raised power minus t down there. That's what you have in that situation. And that's exactly what is right here. So e raised power 2 to 2 e raised power minus t. And then we have diagonalizable matrices. So we already saw that diagonalization makes some procedures very simple. If you imagine raising a matrix to power 10, but by diagonalizing, you can just make things easy. So if A can be written as PDP inverse, then e raised power 80 can also be written as P e raised power DTP inverse, where D is a diagonal matrix of the eigenvalues, like we already know, and P is the matrix containing eigenvectors as columns. Of course, you have to be sure that the eigenvalues in D, if the eigenvalue in the first column in D must correspond with the eigenvector in the first column in P. That's the way it can be consistent. So we have some diagonalization procedure. First, you find eigenvalues, find eigenvectors, form matrix P. That's made up of the eigenvectors. Then form matrix D made of corresponding eigenvalues and compute e raised power 80. So in case you don't know how to do that, check out the video on diagonalization. That helps with that. Diagonalization of matrices. So look at this example 2 now. Okay, I think I need to do it step by step. So if you look at this example, to solve x prime, that's 3102x. The initial condition is 0, 1. So what do we do? If you find the eigenvalue of this, because it is a triangular matrix, you can already read of the eigen. So because below the principal diagonal is 0, so it means the eigenvalues are simply 3 and 2, like this. So the matrix of PD now, of course, to find the matrix of PD, you now need to look for the eigenvectors. We already saw how to compute eigenvalues and eigenvectors. So we have eigenvalues here. So the eigenvectors, if you go for that, you get 1, 0, minus 1, 1. Okay, well, I mean, since the job has been simplified for us, maybe I'll just try. So the diagonal matrix is just for eigenvalue 1, you have 3, 0, and then for the other one, you have 0, 2. So, but this one, you may be wondering, of course, I've explained how to do, but I think I'll just take the pain to still do it here. 3102, we want to find the eigenvalues and eigenvectors, 3102. So for 3102 now, you have 3102, okay? Call that matrix A, right? So the eigenvalues, eigenvalues, the eigenvalues are lambda 1, which is 3, lambda 2, which is 2. You can also say lambda 1 is 2, lambda 2 is 3. So anyhow, but just make sure that everything corresponds. So that's easy because this is the principal diagonal, and below it, all we have is 0. So we can just read it off straight. So if it was a 3 by 3 matrix where you had 3, 0, 3, 2, 1, all right, 1, 4, okay, 3, 2, 1, 0, 4, 5, then 0, 0, 0, 2. Okay, this is also the principal diagonal. Everything below it is 0. So it means that the eigenvalues will just be 3, 4, and 2 here. So if you don't have to compute it, you don't have to stress. So these are the eigenvalues now. So the next thing is to find the eigenvectors. So to find the eigenvectors, to find the eigenvectors, you know, we do it. There's an eigenvector corresponding to each eigenvalue. So we say for lambda 1, which is equal to 3. So what do? We know for eigenvector, we just need to solve this. We have A minus lambda I into V equals 0. So, and what is our A here? 3102. So that's 3102 minus our lambda here is 3. Okay, so that's 3 times the unit matrix, which is 3003, like this, multiplied by V, that's V1, V2, or if you like, call it XY, and that will be 0, 0, like this. So if you tidy this up, you have 3 minus 3, 0, 1 minus 0 is 1, then 0 minus 0 is 0, 2 minus 3 is minus 1, into V1, V2 equals 0, 0. So what do we have here? Because this is two rows, you write V1, V2 twice, V1, V2, V1, V2. Okay, so V1, V2 now you have 0, 1. This other one you have 0, minus 1. Okay, and that is equal to 0, 0. So if you multiply this out, so the V1 is gone in each case. So you have V2 equals 0 or minus V2 equals 0. In each case, it's simply tells us conclusively that V2 is equal to 0. And we have a free variable. So V1 is free. So if V1 is free, you can assign it any value you like, especially 1. So, so taking taking V1 to be 1, we have V1, V2 to be the same thing as V1 is 1, so V2 is 0. V2 is conclusively 0. That's why we have V1, V2 to be 0. For eigenvalue 3 now, so you see eigenvalue 3, so for eigenvalue 3, we have uh, 1, 0, as you can see there. So that's why we have that 1, 0 right here. So you have to be sure because 3 is here, you have 1, 0. If 2 was here now, the other eigenvalue we get is what you're going to get here. So for eigenvalue 3, we have that 1, 0. So that's for eigenvalue 3. What about for eigenvalue 2? Um, for lambda 2, which is equal to 2, again we have a minus lambda I multiplied by v equals 0. Don't forget, we're looking for this v again. So what is a now? A is 3102, I believe. 3102. 3102, yes. Then the lambda now is 2. So we have 2002 like this into v1, v2, and all of this is equal to 0, 0. So what do we do? 3 minus 2. 3 minus 2 is 1. 1 minus 0 is 1. 0 minus 0 is 0. 2 minus 2 is 0 into V1, V2, and this is equal to 0, 0. So in this case, we want to expand this. 3 minus 2 is 1. 1 minus 0, yeah? So 2 rows, it means we have V2 twice. So V1, V2, V1, V2. And then you put 1, 1 over it. This 1, 1 up here. Then 0, 0 down here. All of that is equal to 0, 0. So for the second set, there's nothing important, nothing useful there. So this is V1 times 1. That's V1 plus V2 equals 0. So this whole thing just goes away. So here we have an equation with two variables. So in this case, we are going to have infinitely many solutions. But the easiest way to go can be to say V2 is equal to minus V1, right? So in this case, we can just say if V1 is equal to 1, then V2 will just be minus 1, okay? So we simply have that V1, V2 is equal to 1 minus 1. So overall, we then have we have when the eigenvalue is 3, we have 1, 0. Okay. And when the eigenvalue is 2, we have 1 minus 1. And that is why to for A, which is PD P inverse, we can then form the matrix P now. It is the matrix of the eigenvector. So 1, 0, 1 minus 1. So we have 1, 0, 1 minus 1. And for matrix D, so matrix D is the matrix of eigenvalues. So the first eigenvalue. So make sure the first eigenvector, so you have to make sure you have the first eigenvalue. So you have 3, 0. And for the second one, you have 0, 2. That's how it can be. So that's how we can write A as PDP inverse like this. So going back here now, so I have explained how all of that should be. So we have our P, we have our D, then we can then compute e raised power dt. Because don't forget also that e raised power at is equal to P e raised power dt P inverse, right? So here now we have e raised power dt. This is d here. So that'll be e raised power 3t 0, 0, e raised power 2t. Then the final solution will then have to be so the x we are computing now e raised power dt multiply by 0, 1, I think, multiply by 0, 1. What the x of t? We compute EAT. So the final x of t here is actually e raised power dt multiplied by 0, multiplied by 0, 1, yes, multiplied by 0, 1. So we have so this gives e raised power 3t e raised power 3t minus 2t, then e raised power 2t down here. I think there's more to this than this. So we compute e raised power 80, right? And then that goes, okay? So we have that solution right there. So we have the Jordan form. The Jordan form becomes useful when you cannot uh diagonalize your matrix A. So if A is not diagonalizable, A becomes PJP inverse. Instead of D, it becomes J. J in this case is now the Jordan matrix. And for the J now will be lambda, lambda, and then you have 1 here. So in this case, we have that e raised power jt is e raised power lambda t into 1t01, like this. So example of a Jordan case now. Imagine x prime is 2102x. Then e raised power 8t will just be e raised power 2t into, this 2 will come out. So you have e raised power 2t into 1, 1. Then t will now replace this. So the general solution then becomes x of t equals e raised power 2t into 1t01 multiplied by c. So c1 can be c1, c2. So like the solution, that a kind of b thing we used to have, or that 1 0 kind of thing we had. So if you multiply that out now, you have e raised power 2t into c1 plus tc2. Then x2t is c2 e raised power 2t, like that. Now, still talking about linear algebra in differential equations, we can talk about phase plane behavior. So for x prime equals ax, behavior depends on eigenvalues. So if eigenvalues are both positive, you have unstable node because you have explosion. You have the system growing boundlessly. If both are negative, you have stable nodes because you have stability, you have convergence. So in the case of unstable node, you have divergence. Then if they are opposite signs, you have a saddle, like you have a kind of confusion. So if you have complex eigenvalues, you have spirals, maybe spiraling in or spiraling out. Then if the value is 0, then it's a center, like a limit cycle. Like I think I explained that in the previous video. Okay, maybe I should do some drawing to explain as much as possible. So imagine now we're talking about mm, stability and all that. So we're talking about stability in this case now. So we say that, and they are based on eigenvalues. So if lambda i's are both, if lambda i's, okay, let's you given lambda 1, lambda 2, okay, um then we have the first case. If lambda 1 is greater than 0, and lambda 2 is greater than 0, we have unstable nodes. What that means is that if you have a particular point like this, so all the points will go out of that, you know. So you have outgrowth from there. So there's no convergence into that point. So that's that first one. And then secondly, number 2, if lambda 1 is negative, that's less than 0, and lambda 2 is less than 0, you have what we call stable nodes. Just like what we have right here, you have stable nodes or stable node. Stable node. So that's stable node. Then here you have that's unstable node up there. Here you have stable node. What that means is that you have this node here. It's stable because everything is coming into it. You have convergence into that point. You have convergence into the point. So that way it talk about a stable node. Okay. Then you can have a saddle if you have conflicting signals. Say if lambda 1 is greater than 0, lambda 2 is less than 0. So this one is going towards convergence, it's going towards divergence. This one is going towards convergence. So, but overall, we call it a saddle. Call it a saddle point. So it's more like a saddle node in short. So imagine the node now. So you have so it's more like this is coming and it comes here, you have some points coming, they come here and they get diverted away, trying to do as good as possible. So they try to come and they get diverted away from that place. Hmm, let me try better. So this goes away. They can't stay. Then this comes and goes away. This comes and goes away. But then on the other side, you have some points coming and entering. So coming and entering. So that's like a saddle. So you have conflicting signals, if you like, to use that idea. Then you have if you have complex if you have complex eigenvalues, okay? For now, if lambda 1, lambda 2 all belonged uh, uh, in the form in the form A plus BI. That's complex now. So because of this complex part. So this part will now determine what you are going to have. So generally speaking, if you have this, you are going to have spirals. So spirals can be of this anything like this. But then the direction the spiral goes will be determined by this A. Okay? So if A is greater than 0, you have a spiral that grows outward. So imagine this spiral now. So okay, let me try. So you have the spiral growing outwards in that direction. So the direction is what matters in this case now. So the spiral is growing outwards. It's growing outwards. Um, growing outwards. Growing outwards. So you have an out what that you have outward spiral, right? Outward spiral. Okay. Outward spiral. When I talk about equilibrium dynamical systems, this would be better understood. Then on the other hand, if A is less than 0, you have inward spiral. So imagine it's still the same kind of spiral, except that now the direction is different. Or maybe if you draw it from outside now, so it's like you have inward spiral. So it's converging towards something. So in this case now, so the direction is reversed. So you have something going inside. So you have this going inside. Okay. So going inside. Okay. Then this is going inside. So you have an inward spiral. Okay. Inward spiral. On the other hand, what if the lambdas are 0? Okay. So finally, if that's 5 now, if lambda 1 is 0, lambda 2 is 0, or something like that, so you're going to have a center, okay, or what some people call limit cycle. So that means you have the node here, but then you just have an orbit, you have it, you have an orbit around the center. So the orbit's just moving around the point. So this is what we call a center. I think this is also what is called limit cycle. Okay, so these are the possible kind of stabilities you can have depending on the eigenvalues, uh, the possibility of eigenvalues that might be. Okay, so did I indicate that this is for limit cycle? That is, yeah, if lambda and lambdas are 0, exactly. So if the eigenvalues are 0. Okay, so look at this now. A is 0 minus 1, 1, 0. So the eigenvalues are plus or minus I. Automatically, because they are plus or minus I, this produces oscillations. The oscillations are what we call spirals, actually. So they are called spirals. So then we have general algorithm. So to solve x prime equals ax, what's the first thing you do? You find the eigenvalues of a, then 2, you check diagonalizability, then 3, you compute e raised power 80, 4, you apply initial condition, which is and then you apply initial condition, and then you get x of 2 to be e raised power 80 multiplied by x of 0. So some key takeaways from this will be like this, that systems of ordinary differential equations become matrix equations. Solutions use matrix exponentials. Eigenvalues determine behavior. Diagonalization simplifies computation. Jordan form handles special cases when you cannot diagonalize a matrix. And the main formula is that x of t is e raised power at multiplied by the initial condition x of 0. So you can try this out on different problems. To solve each system using matrix methods, x prime is 1003 x. So of course, find the eigenvalues are 1 and 3. Then you can find the eigenvectors to see the possibility. So I mean, uh, yeah. So check if they can be diagonalized and do all of that. Okay. So that's 1 and 2. You want to try. Then 3 and 4 now. Same. Find the general solution. So yeah, we are looking for general solution there because there's no initial condition, but here there's initial condition. So you're going to get a particular solution. If this answer solution is not general because you have the initial condition. Classify the equilibrium at the origin. Okay, so you get the eigenvalues, and then so from there you can use the eigenvalues to classify the equilibrium, to classify the equilibrium. Then here we are solving this problem. 7 and 8 now. You have find the general solution. Then here you describe the motion based on the equation you get. Then 9 and 10, you have find the eigenvalues and classify the system. And you have a 3 by 3 system, so you can also solve this same approach all the way. So look at the examples and try your hands on this. Let me know how helpful this is for you. And if there's something like to try out, feel very free to let me know. If you have subscribed already to this channel, I must thank you so much for doing that. If you have not subscribed, what are you waiting for? Go ahead and subscribe. Hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of this channel by clicking on join. That gives you some special privileges, like seeing some videos alone or seeing some videos first. And of course, you can request for my PDF notes. I can consult for you on something that interests you here. We may have a one-on-one session of teaching on any of these things, depending on your level of membership. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.